Hi, welcome to the second part of our Splinter meeting dedicated to machine learning for EPRV. Today we are going deep. First of all, a small disclaimer. I love talking to audiences, but I don't feel too confident with the language, so I wrote everything here. Yep, even the shows. Sorry if I look like a politician giving a speech, but I think it's for the best. So let's begin with our first presentation. This is the disclaimer. So a little bit about me and our group. My name is Luis Agustín Nieto. I'm doing my PhD in applied science under supervision of Rodrigo Diaz. Our work is focused on the development of machine learning solutions for applications in astrophysics in general and exoplanet in particular. I'm a computer scientist with an HPC background, and also I'm current world champion. Yes. Sorry about that. I'm not really a soccer guy, but I need to fit in the Argentina stereotype. Well, the topic we discussed on the last meeting, we started on machine learning the hard way. That is reading books, preparing notebooks, and teaching at the university and in the private sector. You know, maybe things have gone too far, and now we have a new data science degree, and Rodrigo is the head director. You don't need to go that far, but teaching is a good way to learn, and the different needs between industry and university force you to learn things in a different way. Also, you can go in the interdisciplinary way. Just send a catchy email to the computer science or math department. For sure, you will find a geeky person who loves Carl Sagan and wants some problems to solve. At least that's worked for me. Okay, some similarities and differences with classical machine learning. When we say deep, we are talking about neural networks with more than 2 hidden layers, right? Like a multi-layer perceptron. This kind of techniques can be used on more complex or specific problems, but usually needs more data, training time, and hardware. The more used libraries are TensorFlow, Keras, and PyTorch. We have several parameters to tune, a lot, and we're still having the black box issues, same golden rule, train, validation, and test, overfitting problems, and no general rules for architectures, right? Just good practice. We're gonna talk about this in a moment. We will have 3 talks today. I put myself at the end just in case we are running out of time. And I need to rush for these talks. I'm going to use 2 main topics, convolutional neural networks and autoencoders, right? So let's begin with the CNNs. Like many things in the area, the concepts of convolutional neural networks came from biology. Experimenting with cats and monkeys, they find out that some neurons in the visual cortex have a small receptive field and react to simple patterns. Other neurons have more large receptive fields and react to more complex structures. And several researchers along the time emulated this mechanism with this architecture that was born to work with images, but can also be used with one-dimensional data that has a spatial structure, like text or time series. Yes. So let's see what happens if you want to use a neural network, a classical one, with an image. We need to flatten the image. And by doing this, we lose all the spatial structure of the image, right? If we use a CNN, in the first layers, we have neurons that see a small region of the image. And as we are going deep, the neurons can see larger regions of complex patterns. For example, if you are looking for faces in an image, the first layers can react to lines or circles, the middle ones to eyes and ears, and the last one to a full face. That's the idea. This receptive field, this one, what the neuron can see, is done by defining an unusually small kernel. It's not a GP kernel, it's just a small matrix, and striding it around the image to generate what is called a feature map. all units in a given convolutional layer, actually in a filter, share weights. So each feature map is made with a different filter. Right? Okay. Let's see. Okay. So here's an example of the classical NIST data set. There is an image of 28 by 28 pixels, and we generate the first layer by applying 32 filters of 3 by 3 kernels. This one. And in the right image can be seen that each filter is different and generate a different feature map. This is an example from the Heron. So we have a feature map with a vertical filter and another one with an horizontal filter. If you have color images, just add another dimension to the kernel, and in the feature map, there all will be added. So the layer keeps the same dimension. I mean this one. So the kernel is 3D, but in the first convolution, it goes 2D. Okay. As you can see, things grow up very fast. One solution is using pooling layers to reduce dimensions and keep the important features like this here. Is to reduce dimension and to keep the important features. In this particular case, a max pooling layer of 2 by 2 is used, so it keeps the maximum value for a region. So we apply the first convolution here. We have a lot. We began from 28 by 28 to a lot of neurons, so we have to reduce it. In this case, it's max pooling. There's another kind of pooling, but max pooling is, I think, is the most used. So this is a typical CNN architecture. It is done by stacking a few convolutional layers and then a pooling layer, convolutional pooling, so and so on. At the end of the network, you have extract, hopefully, or here, you have extract the more complex features. So you just need to add a regular neural network to work with them. And at the end of the network, you have to add the layer according you are working with, right? It's a regression, it's a classification, etc. So this is one of the good practices when working with convolutional. Okay, let's go with autoencoders and stack autoencoders. One of the most interesting architectures. Autoencoders can learn dense representations of the input data without any supervision. This is called latent representations. This can be used for dimensionality reduction, generative models, feature selections, feature detectors, and unsupervised pre-training of deep neural networks. Convolutional autoencoders can be used for images, and recurrent autoencoders can be used for sequences. Let's see how they work. So they are just neural networks with the same size in the input as in the output, but with a bottleneck in the middle. They are trained to reproduce the input in the output. And the architecture forces the encoder part, this one first, to learn an efficient form of representation. With this, the decoder learns how to generate data that is similar to the one that was trained into, and both parts can be used separately. The same idea can be used for more encoders, for more complex problems, and with particular kind of layers like convolutional software, right? So to finish, a couple of references we use all the time. The classical all-time load by everyone Bishop, the more practical approach of the Heron, a paper with a deep approach to the hyperparameters, and a very interesting and classical paper about how to get interpretability in the CNN, right? another topic we discussed on Tuesday. So thank you all for listening, and let's hear our speakers.
Oh. I don't know.
Versus on the other side, which does not make sense.
Oh, let me split it. Swap this better.
Yeah, what's that? Amazing. Okay. Is that okay?
Yeah.
That looks good?
What about online speakers? Can online speakers see the full screen?
Full screen?
Yeah, can people on Zoom see the full screen? Okay, great. Thanks. All right, thank you. My name is Jinglin from Penn State. Today, I'm going to talk about parameterizing and modeling stellar variability in sun as a star studies. So I won't go as deep learning, but we will see. So to start with, why do we need to parameterize the stellar and instrumental variability? Of course, we are in the EPRV era. We want to disentangle the stellar variability from the planetary RVs. But on top of that, we also have instrumental and environmental variability. Both the stellar component and the instrumental component can affect the line variability. So in order to parameterize and characterize these line variability, we need to extract the spectral information that is only sensitive to the shape of the lines. So people, the community have been using line activity indicators like H alpha, calcium H and K, or they extract information from the full width half maximum and bisector span from the CCF. And recent papers uses the scapos or Fiesta to parameterize the line profile. So what I'm going to do is to use the Fiesta method that decomposes the line profile, the CCF, into a set of orthogonal Fourier functions. And we use the radial velocity shift of these set of Fourier functions to parameterize the line profile deformation, and so as to understand how the stellar and instrumental variability affects the radial velocity. So what Fiesta does, as it shows here, we have basically a set of orthogonal Fourier functions, and in comparison, what scapo does is also extracting the information that is insensitive to the Doppler shift. So quite interesting here is that the first few modes of Fiesta and the first few principal components of the scapos that derived from the ACF, the autocorrelation function of the CCF, is the same. And I think it is not coincidental because we want to extract the information that is not sensitive to a line shift, and then we end up in the same basis functions in both Fiesta and Scaples. So to give you a further understanding of what Fiesta does, so for a pure line shift, as the left diagram shows here, all the Fiesta modes or the Fourier modes would be shifted at the same amount. But for line deformation in the right diagram, different Fourier modes will be shifted at different pace. So we can basically use this difference in the radial velocity at different modes to parameterize the line deformation. This is an example of a slope simulation of a dark spot. And so imagine the stellar surface, imagine the star is rotating and the spot comes and goes. So we see this radial velocity curve on the right. But if we measure only the line centroid, we only measure one radial velocity, which is the apparent radial velocity. Instead, we measure the radial velocity shift of each Fourier modes. Then we would have different radial velocity shifts for different modes. So this diagram shows the radial velocity shift of the first 5 modes. And because each mode follows the Doppler radial velocity shift. So if we subtract the radial velocity shift of each mode of the RVFTK by an apparent radial velocity shift RV Gaussian, then we can subtract out the Doppler radial velocity shift. And what is left at this delta RVK would just be sensitive to the stellar or instrumental effects. And that's why we're going to use this delta RVK to parameterize the line deformation. So part 2, we will use multilinear regression on these Fiesta indicators, the delta RVKs. So for the Harps North solar observations, the 3 years Harps North solar observations, we can extract the line deformation using the delta RVKs. And as you can see here, the first row is the RV time series. The following rows are the delta RVKs that traces the line variability. And even though the RV time series looks kind of continuous, in the first 2 modes of the delta RVKs, we can see these jumps in the time series corresponding to the detector warm-ups that Xavier Dumus mentioned earlier in the conference. And on top of that, we can also see the long-term RV trend in these delta RVKs in the first 4 modes, corresponding to a long-term magnetic trend. And as you can also see that it's correlated with the RV time series. And when we move to the periodogram, we can see that the solar rotation period and its harmonics start to occur in 4th component and also the 6th component. And that indicates that these components would chases the stellar rotation effects. So basically what it's saying is that using this Fiesta decomposition, we can chase the stellar variability at different length scales that occur in the CCF. The higher the modes, the smaller the scale it chases. And what you can also see is that some of these time series are correlated. So in order to extract the information, we do a PCA so that each principal component hopefully represents a different mechanism. So this is just a PCA analysis on the multiple time series of the delta RVKs up to a certain limit. And as you can see, the first component still chases the long-term trend, and the second component chases the line, the stellar rotation effects and some long-term effects. We don't know much about the third component, but it's probably related to line diffusion that caused by the Earth orbit. And furthermore, we can separate out the long-term effects and the short-term effects using a low-pass filter. So basically what it does is to separate the effects below 100 days and the effects over 100 days. So the effects below 100 days would attribute to the solar rotation effects. And then we can use these 6 components as features to model the time series. And before we do that, we also shift these 6 features by days to study whether these features have a lag compared to the time series. So let's say here at lag 0, we have 6 features, and then we've shifted by 1 day, 2 days, etc. And then we have like 6 multiplied by 11 features. But because these long-term features would be insensitive to a shift, insensitive to the lag that we introduce. So we only fix these long-term features at lag of 0. So altogether, we have 11 times 3 plus 3 features, altogether 36 features. And then we use these 36 features to model the stellar variability RVs. And what it turns out is that these are the variance. So this is a variance percentage. So all these numbers add up to 100. And the largest number here, 81%, means that this feature, this long-term feature, accounts for 81% of the variance in the RV time series. And these first 3 components are due to stellar rotation. So we can also add up these percentages to see how much the solar rotation effects would contribute to the total RV variability. And that turns out to be about 0.5 meters per second or 7%. And also we reduce the RMS from 1.89 meter per second to 0.94 meter per second after this multilinear regression. And just a little message on besides the multilinear regression, we also do a regularization on the training and testing data set. So basically we penalize loss function by introducing this lambda on this, because we don't want all the coefficients to occur. We want only the important coefficients to show up in this multilinear regression fit. And so as lambda increases, the loss function in the training set will definitely increase. But at the beginning, the testing set would become, the loss function of the testing data set would decrease, because when we increase the lambda, the penalization of the model becomes more robust. So in terms of the testing data set, it becomes more robust to overfitting. But when lambda reaches some threshold, both loss functions of the training data set and testing data set would increase, because it's lambda contributes to the loss function. So at some point, we choose a proper lambda to represent the robustness of the model at about 0.05. One important message of this method, of this result, is that we also observe a 3 days lag of the indicators compared to the time series, as you look at the rotation effects here. So the coefficients, the variance focus concentrates on the 3-day lag. And to do a comparison between the Fiesta indicators and full width half maximum and bisector span, we do the same analysis, but instead of, we don't need principal component analysis because we only have bisector span and full width half maximum. But we still do a low pass filter to separate the stellar effects, the rotation effects, and the long-term effects. And this is the result similar to the previous one, except that the weighted RMS increased a little bit to 1.04 meter per second. And we observe a one day lag in the full width path maximum and a 3-day lag in the bisector span. So moving forward to the machine learning approach, we want to see whether using a automated or machine learning approach would derive the same results. And it turned out to be, so in this case, we have only one layer and we use linear regression only because it's linear regression, so it doesn't make sense to add multiple layers. What it turned out is that we don't see this 3-day lag anymore. And also the residual WRMS, weighted RMS has increased. And it's quite surprising that if we don't know the physics of it, we just apply a machine learning approach to this problem, we would end up something, but the result is not that interpretable. This is just a comparison between a traditional approach and a machine learning approach, where using the traditional approach, we can see a 3-day lag, but using this pure machine learning approach, we don't see this 3 days lag, but it's kind of scattered everywhere. We also added more layers and tried other activation functions. It improves the performance a little bit, but not substantially. And we think that the residual about 1 meter per second is due to other effects like granulation or supergranulation. And also with other activation functions and more layers, it's hard to interpret the coefficients or the weights. I'll quickly talk about the planet injection recovery test in New solar data. So this is the 2021 New solar data time series, which has a slightly, well, actually a much better daily beam RMS at 1.1 meter per second compared to about 2 meter per second in the Harps North. And we want to use the RVFTK as features to predict a injected Doppler RV because the RVFTK traces the line variability and also it is sensitive to the injected RV as well, the Doppler RVs. So this is just the result showing that the residual RV, which is the difference between the prediction and the true RV as a function of the injected amplitude, and it shows that there's a floor at about 0.62 meter per second. Lessons learned. So we need to pick the right or better features. So comparing between Fiesta and bisector span with half maximum, Fiesta decomposed the line profile into orthogonal basis functions. So first of all, it's orthogonal, so it would provide more information, more complete information than bisector span or with half maximum. And second of all, the Fiesta RVs has a unit of radial velocity. So we are using radial velocity. So whether we need to understand this black box, I think it actually depends what the problem is. So in the first scenario, if we were to study this lag, then we definitely need to understand what each coefficient or weight means. Then we need to understand what this black box is doing. But in the second example, where we just do a planet injection recovery test, we want to recover the injected RVs, we don't need to know what this black box is doing because as long as it has a good prediction, then it's doing its job. I think that's the conclusion. I'm happy to.
So your mic and then bring it back to you.
So we can share the mic. This is a very nice talk, Jing. Thanks for giving it to us. I was wondering what the difference is between your traditional approach and your machine learning approach. Like, what are the different inputs? Because it seems like the traditional approach is like a linear regression on these hand-picked sets of features that you've figured out using your principled approach. What are the features you're using for machine learning?
Thanks. That's a very good question. And I should have the approach method, except that we feed into a machine learning, like using TensorFlow and the Keras machine learning package, and we think that it's doing the thing, but it's actually not. On one hand, I think it's because we have this training and testing split issue, so that that would kind of increase the residual mass a little bit. And on the other hand, there would be a lot of hyperparameters that we have to train, which could. Only if. Yeah, but the problem is that whether we can optimize these hyperparameters to represent what the problem is, like whether we can optimize them to explain the physical mechanisms of feature, that's a question.
Introduce you for a second if you want. No, you're all good. Yes, great. Okay, so our next speaker will be Jen Liang. Please welcome.
I'm Yan. I'm a graduate student from Princeton University, and today I'm very excited to present my work on Astra, a deep learning tool for mitigating stellar activity in EPRV measurements. So let's get started. We all know that RV precision is limited by stellar activity, and the Doppler factor is about 10 centimeters per second, but the apparent radial velocity induced by stellar activity can be easily order of magnitude larger than that. Realistic modeling of activity on the stellar surface at the spectral level is extremely challenging, if not impossible. So what do? How can we utilize the wealth of the information contained in the full stellar spectrum? Well, as you can probably tell from my talk title, my solution is unsupervised deep learning. So you might found it to be a crazy idea, but in the rest of my talk, I'll try to convince you that this is not that crazy to do. So this project is actually inspired by my previous work on trying to auto-encode galaxy spectra, in particular, which to use a number of 10 vector, a small number of parameters to represent 500,000 Sloan galaxies. And we are facing a very similar challenge where we have to disentangle galaxy redshift from the internal spectral shape of the galaxies, which encodes galaxy type or all the physical information that we care a lot about. So we ended up building an autoencoder model to represent Sloan galaxies using just 6 numbers, and we achieved fantastic results for reconstruction. So I just thought, why not try and apply this to stellar spectra? Because if we can similarly build high quality spectra for stellar activities, we are effectively getting RVs for free. So this, what's making this even more promising is that the terror hunting experiment is about to employ an intensive sampling strategy and collect data for nearby stars on a 10-year baseline. That way, we can have a very accurate tracking of stellar activities and provide a lot of data sets for me to train on. So Astra. So it's an unsupervised deep learning approach, and it takes full spectra in the observed frame. It does not require any ground truth RV information for training and does not rely on specific physical models. After training, you will get radial velocity estimate. You will get generalized activity indicators, which we call latent vectors, and also unshifted internal stellar activity models for each of the input spectrum. So if you provide me with 100 I will give you 100 models. So before I get into the detail, I will try and give a bit of teaser. Here I show how Astra has been used to recover a 10 centimeter per second Earth-like signal in the presence of stellar activity noise, which is 30 times larger than the signal we were looking for. The recovery is basically perfect. We achieved a photon noise limit in the RMS. How is that possible? I will try to give a quick introduction to the core component of this algorithm, autoencoder. So basically, for those of you who are not familiar with machine learning jargon, I will just say autoencoder is a fancy PCA. You can think of encoder as a data compressor. You just take whatever input signal, here a handwritten digit 5, you will be compressed by the encoder, represent in terms of like 2 or 3 numbers. and it will be used by the decoder to reconstruct exactly the same input signal. Then you might ask, why do we need an autoencoder? Why not just do PCA? Well, this is because our model needs to be in the rest frame. So while our input model is in the observed frame, so features can be moving around, we always want the decoder to construct a stable Doppler shift invariant rest frame model for stellar activities. So the encoder must be smart enough to pay no attention to the location of the features and only concentrate on the shape of the features. So another important component is the radial velocity estimator. I will try to be fast and explain this in a minute. The input signal will be processed by the kernels moving around and searching for features in the 1D spectrum, and the output of the convolutional layers will be a vector of 1,000 dimensions. It will be called a feature vector, and the feature vector is then fed into the multi-layer perceptron, which will use the feature vector to try and infer the radial velocity from it. So just to put everything together, in the ideal world, we will have a spectrum autoencoder, which is responsible for searching for rest frame features, faithfully reconstruct the activity spectrum always in rest frame and never be contaminated by any Doppler shifts. We will also have a RV estimator, which is responsible for giving us an RV estimate. We will combine the output of the two pipeline and redshift the rest frame model to the correct amount and build a reconstructed spectrum. At the end of the day, we always want the input spectrum to match the reconstructed spectrum to make sure that it's doing the right thing. So the outputs of the network will be an RV estimate, an activity spectrum, which is the comprehensive rest frame model for stellar activity, and also a latent vector, which encodes only intrinsic line variations and should be invariant against Doppler shifts. So far, I've made a lot of statement about what it do it. So the last function we used for training this network are three components. The first one is just the standard fidelity loss, which says the reconstruction should always match the input. Very easy to understand. The second one, and the most important one, I think, is the RV consistency loss. We are training on unsupervised networks, so there are no true information for training the RV estimator. So what do? We will teach the RV estimator what a Doppler shift would do to the spectrum. I will explain it in detail soon. The third term is just a regularization loss, which always tries to push our activity spectrum to 0 to avoid overfitting. So let's get into the core of this algorithm and think about how to teach the RV estimator the Doppler RV, how to disentangle Doppler RVs from some spectral perturbations. For each of the observed spectrum, we do not know the true RV, but we can always inject some artificial radial velocity offsets. On the right-hand side, I'm showing a random Sloan galaxy spectrum, which I stole from my previous project. The black one is showing a input spectrum at redshift 0.02. The blue spectrum is when I just artificially stretch the input spectrum and resample it to the observed wavelength. Finally, we add some random noise to random locations to mimic some instrumental glitch that might confuse the encoder and help to train a more robust encoder. Lastly, we will use the RV estimator to estimate the RV offset between the input and the augmented spectrum. So if you take a closer look at my RV consistency loss, you will find that I'm just comparing the predicted RV offset to the injected RV offset and I ask for agreements. So by training on augmented data, I can generate an effectively infinite number of samples for training, and we can always achieve desired precision or exploit all the information content in the spectrum. So our method has been tested on simulated data set. I will try to explain how we build this data set. We use SOAP 2.0 for simulation of stellar activity on cross-correlation functions. And this code accounts for two physical effects. The flux effect, which refers to the temperature contrast between the active region and the quiet region, and the inhibition of convective blue shift, which will always make the active region appear redshifted. But we only have CCFs. How do we construct full spectrum? I've proceeded with a pretty simple strategy. We first build a quiet spectrum by randomly generating a line list, randomly drawing some width and depth. Then we calculated the active CCF with 4 random active regions located on the star, and the parameters are drawn from this table. Finally, we just perturb the quiet spectrum line by line by multiplying the CCF ratio, which is defined as the active CCF divided by the quiet CCF. On the right, I am showing some examples of the CCF ratios for a spot and a plage during the stellar rotation surface. So to test the performance of Astra, we simulated 1,000 different spectral perturbations at different times, and we injected 10 centimeter per second RV signal to the simulated dataset. Finally, just to make the live hour encoder even harder, we injected 3 centimeter per second, 0.3 meters per second photon noise, which is 3 times larger than the signal we were looking for. So let's see how it performs. Well, the reconstruction for simulated data, I would say, is just perfect to my eye. The thin green line here show the input data with photon noise and behind the true spectrum that we generated for this sample. So if you measure the goodness of fit using a chi-square metric, this is almost as good as the truth. The perfect reconstruction suggests that our latent vector contains full information required to reconstruct the intrinsic spectrum, and it can be interpreted as a generalized activity indicators. So does it mean that we can just read off the RV estimates from our IV estimator and look for some beautiful Keplerian signal? Not yet. Finally, we need to detrend RV estimate with our latent vector. In the ideal world, of course, the Doppler radial velocity for a star should be uncorrelated with the internal activities. But in real life, the measured radial velocities are inevitably correlated with latent positions. So our measured or encoded radial velocity will be a sum of the true Doppler signal and a shape-dependent RV offset. How do we correct for that offset? So we'll proceed with a strategy that we perform a Gaussian blur of the RV estimates in the latent space and use the Gaussian blur to represent the trend. We subtract this trend to hopefully recover the correct Doppler velocities. On the left is just a random 3-dimensional figure of my latent distribution. The blues are the encoded original or input spectrum, and the red represents their artificially redshifted augmented spectrum. So I will try to explain why this is necessary. So during training, RV estimates are only calibrated for the same activity type. On the right-hand side, I'm showing a 2-dimensional latent space with 9 data points. They represent different activity types, and they're nicely clustered together. If we plot encoded radial velocity with one of the latent dimensions, we will see that although within the same activity type, RVs are well calibrated, there's no mechanism to prevent a drift or a relative RV offset depending on the shapes. So how do we correct for that? As I said, I am employing a strategy to just average over similar activity types, and we can get a pretty good estimate of where the RV offset, the bulk RV offset, depending on the latent position, should be. Subtracting or detrending the measured RVs with this estimated bulk offset, we are studying this in time domain, we should see a beautiful sinusoid. So here, I'm just showing how this performs on a simulated data set. On the left-hand side, I'm showing the apparent radial velocity was just randomly scattering because I injected some white noise to the star. And on the right-hand side, I'm showing how Astra successfully recovers the signal in a very beautiful way. The RV scatter has been reduced to a limit that it's only due to photon noise. So we also performed a MCMC sampling to retrieve the parameters. The retrieval seems to be pretty satisfying to me. Finally, we performed one additional test. So stellar activities can have time structures. In here, the blue curve show the fraction of active area on the stellar surface. So one will be 1% of the total stellar surface is active. You can see that the blue curve changes continuously and coherently when the spots come and go. Algorithm has no problem handling time structures, although it does not utilize any time domain information. On the right-hand side, you can see using just 200 spectra, we again recovered a beautiful 30 centimeter per second signal, which is even comparable to the injected photon noise. And we also achieved the theoretical limit. If we plot the signal in the parallelogram, we will see a beautiful peak at the correct location. So here's my conclusion. So Astra is under development. Now it uses full spectra, so there's no need to compute CCF or any other metrics. It requires about 200 spectra to perform exploit all the information due to stellar activity. There's no physical model required for activity, which can be a good thing or a bad thing, depending on how you think about it. There's no need for a calibration star. All the data points are self-calibrated. It is not the time domain method, at least not yet. We train Astra in several hours, so it's pretty manageable if you have a GPU. The code will become public and our paper is in preparation. So I just wanted to emphasize that this is an ongoing project, so stay tuned. In near future, I will be applying Astra to solar data, where I need to deal with some telluric features, incorporate time domain analysis, and the hope is that I can build a more physically informed model, like the way we inject the knowledge of Doppler shift to the Eventually, we hope to apply this method to exoplanet hosts, improving characterization and looking to validate some low signal to noise candidate. I can stop here and take any questions.
So nice talk. So I have two short questions. So first, it's a sense, if I get it right, since you put up each line with the same CCF, so what's the extra benefit of using the full spectrum? And the second question is that what's the typical SN ratio your method can work? So for example, like common SN like 80, 100, would that work for this framework?
So the first question is why use spectra instead of just do this? I perturb from in the way that it can be fatter or thinner depending on the random number I draw. So in fact, multiplying a CCF ratio induces different residuals in the spectrum. If I do the same analysis using just one line, then the degeneracy will be severe that you cannot easily disentangle the Doppler shift induced signal from the activity induced signal. They just look like so. And the second question, the second question is about signal to noise. The autoencoder itself is very insensitive to noise level. For galaxy spectra, for example, you can have signal to noise of 1, and the encoder decoder part can still do a fine job in reconstructing the internal model. So our method has been tested with signal to noise 100, 200, 1,000, and it's very flexible and capable of producing internal model for any noise level.
More questions?
Nice talk. You are thinking about applying it to exoplanet hosts, but in those cases, we don't necessarily know what the true velocity is because there could be planets that we don't know about. How can you deal with that lack of knowledge?
Yeah, so great question. This whole architecture is motivated by the fact that we do not know the true RVs for exoplanet hosts. As I mentioned before, the RV estimator is trained purely on RV offset instead of any pivot or line list, or we have no prior physics information. So for exoplanet hosts, I just do exactly the same thing. And I train this network to produce self-consistent RV estimates for the same activity type. Finally, I detrain and self-calibrate all the measurements. So as long as I have enough, or say 200 spectra for exoplanet host, it can be any perturbation, any line profile, it can still do its job.
One more question, Alex? Yeah.
Yeah, I'm just curious how you pick the number of latent space layers like at the center of the autoencoder, and also how you think that might change when you go to like solar data or exoplanet hosts.
So the encoder decoder part is a not very deep network. The RV estimator, as you can see, contains 2 convolutional layers and a 3-layer MLP. We tried varying the number of layers, adding 1 more convolution layers or changing the layers for MLPs. It does not change the behavior of the whole architecture. So my way is that as long as your model or network is flexible enough to represent what you want it to represent, then making a deeper network or shallower network, it doesn't really change the behavior. So,
Oh, you're so good. Next, we'll have Agustín giving us a talk about some of his recent work. Let's welcome Agustín.
Hi, I'm the same guy from the beginning. Now I will present something we were working on. We already submit to astronomy and astrophysics, and it's on the archive, so I give you the link. I don't know if we have enough time, but I will going fast. Okay, I will going slow. In this work, we propose a neural network to replace the computation of the significance of the signal detected with the radial velocity method and to classify it as planetary origin or not. The network is trained using synthetic data of systems with and without planetary companions. We inject correlated noise simulations and compare the performance of the network with the traditional method based on null hypothesis significant testing. The preprint is in the archive, and here is. So, periodograms are often employed to find periodic signals in unevenly sampled time series. Different frequencies are tested and fit into the data. The better the model at the frequency, the higher the power. A statistical test is conducted over the highest peak to address its significance. We call this false alarm probability, or FAP. We simulated a lot of RVs measurements with realistic noise and injected planets into the signals. Those are the details. We're going to check it later. So the basic methodology when working with periodograms, very basic, is to analyze the maximum peak and define if it comes from a significant signal or not, right? If it's the case, the signal is removed and a new periodogram is generated using the model residuals. The new maximum peak is identified and analyzed in a similar fashion, right? This is the more basic approach you can take. That means that the network will be receiving periodograms, will not only receive the original periodograms as input, but also subsequent periodograms obtained in this manner. So, in addition to generating the periodograms of stars with up to 4 planets, we also constructed additional periodograms by removing the signal at the largest peak frequency. Doesn't matter if it's significant or not. This process was performed 4 times for each original signal. This not only serves to have more varied periodograms, but also increases the datasets. So 3 datasets were built. The first one is for training and validation. The second for threshold search, and the third one was for testing. This is the architecture of the network. It receives a periodogram here, the position and the power of the maximum peak. The output is a single value representing the probability that the data was originally created from a periodic signal from a planet. We train it using the cross-entropy loss function until it reached an F-score of 0.88 in the validation set. It's a very simple classical convolutional neural network. So the network and the FAP outputs a number. Both implementations require the definition of a threshold if they are used to making decisions. Before setting this threshold in the network, an analysis of the overall effectiveness of each method can be made and compared with each other. Precision recall curves that show the trade-off between those 2 metrics. These 2 metrics. These curves are constructed by varying threshold for the detection and computer the metrics at each value. The greater the area under his curve, the better the overall performance of the algorithm. Once the general performance has been analyzed, we want to find an adequate threshold for the neural network model. We use the false positives and false negatives of the FAB with its already mentioned classical threshold and use these values to find the range of threshold for the network that gives the smallest numbers of both false positive, false negatives. Okay, in this image can be seen that any threshold value for the network between 0.69 and 0.77 will have a better result for false positives and false negatives. So 0.77 was chosen to provide the most reliable detections in terms of false positives. Now we have a threshold. So with this threshold already set, the confusion matrices and precision recall metrics were calculated over the periodograms of the set 3. For the network, the number of false positives decreased by 28.5% and the precision was improved. Let's make a last comparison by plotting the precision and okay. Yes. I think I was missing. No. Let's make a last comparison by plotting the precision and recall of the signals identified as planets, depending on the power, over set 3. The curves for both methods are similar, but for low power peaks, here, exoplanet is more precise. Now, the same analysis, but with precision and recall, depending on the period. Both methods lose precision in the period range between 30 and 60, but the precision of the FAB drops much more than exoplanet. And on the other hand, the FAB shows a relatively constant recall across orbital periods, while the network exhibits a clear decrease at around the same period range. This particular period range is associated with stellar rotation, and many false positive signals are expected to appear here. Our interpretation is that exoplanet learns to be more careful when leveling peaks in this range, which is the same way a professional astronomer will do. As a consequence, the recall is degraded, but the precision is kept relatively high. So, in fact, it is not a fair comparison because the traditional method is not even intended to distinguish activity from planets, just to claim a statistical significance of a signal. Our machine learning method is hence producing two results at the same time, assessing the significance of a signal and identifying his nature. Obviously, future works shall focus on evaluating the performance on real-time series, both by performing simulation with realistic time sampling and on an actual observed data. A very important thing to try is that the neural network can be provided with rich context to the classification task in the form of additional data, like the stellar rotational period or spectral type. So thanks for listening, and any comments on the paper, I welcome. Thank you.
Questions for Agustín? I have a question. So for like each of the different like periodograms that you're feeding in, do you have like some sense of like what the neural network is specifically like maybe picking up on, or like any kind of like explainability component? No, that's okay. Okay.
We don't try anything closely related to explainability. This is the only thing we can explain. We guessed that the network is being cautious in this range because of the stellar activity, but it's a guess. Yes, it's we didn't see anything remote.
So have you thought about including activity indicators and periodograms for those to help it distinguish between, okay, you got that in there as well? Okay, yeah.
Yes, this is on the next step. Yes.
Well, why did you decide to use CNNs instead of other types of neural networks such as MLP or maybe GAN for this kind of problems?
You might want to wait so the people on Zoom can hear it.
Because first of all, it makes sense, parallelograms with the CNN. It was the first thing we tried and it works, so we kept here, basically. But yes, it makes sense at the beginning. So, and it also makes sense given the network this information, and also makes sense given more information. So it will work better.
So we came up with a couple of like questions to kind of get things started, but then we'll hand it over to anyone in the audience who wants to ask questions, or anyone on Zoom. Feel free to put stuff in the Slack and ask any questions. So just to get us started, for each of you guys, for what you've done, maybe actually we can do a quick round of introductions for.
Okay. Yeah, I'm a postdoc at Penn State University. I'm working on a few projects, one of which is trying to develop deep neural networks using CNNs to measure radial velocities in spectra.
I'm Jinglin, also a postdoc at Penn State. I'm working on two projects. One is the stellar variability RV mitigation, and the other is the PMO oscillations. You can see from my poster 85 and 101.
Hello, I'm a graduate student at Princeton University, and I work on a lot of things, mostly on the interdisciplinary machine learning plus astral field. I work on, of course, mitigation of cell activities using machine learning.
My name is Luis Agustín. I'm a PhD student on applied science in Buenos Aires, and I'm working on machine learning for exoplanets.
Okay, so awesome. So the first question that we had was, what was kind of the primary challenge for each of you guys in successfully implementing your machine learning method or other kinds of statistical method for RVs?
Probably just the whole garbage in, garbage out idea. Just trying to be really careful and make sure that what you feed into the network is not doesn't have any sort of hints of what you know the truth is. Because I was working with the injected planet signals, so making sure that there's no hints of what those are, and making sure that I'm sort of reducing the complexity of the data in a way that doesn't actually reduce the signal.
For me, I'm just picking up machine learning, so I find the biggest challenge is to understand each algorithms and also how to implement it in my research.
So personally, I feel that for machine learning, it's very general solution, but you need to ask the correct question so that it can answer your question. For me, I made assumptions such as wavelength calibrations are perfect, Tayloric subtractions are perfect. These assumptions may not hold true, and this can introduce a lot of artifacts to the learned features. This is the biggest challenge I'm facing.
For me, in this particular case, this is a supervised learning method, right? So if I want to test it in real data, it's a little bit challenged because you have to test it in something you know. So if you know the results, so why you are doing machine learning? So it's that going from realistic to real, it's a challenge.
Okay, the next for each of you, what is kind of your vision for how deep learning methods will play a role in working towards achieving extreme precision radial velocities in the next 10, 20, 30 years?
Well, I think they have a lot of obviously flexibility, and I think with the specific problem of stellar activity, that flexibility might be able to be leveraged to model all these sort of simultaneous effects that have been so difficult for humans to wrap their brains around. I think that there's a lot of work to do, and I think that it's definitely not going to happen in the next few years. But I think I'm optimistic that, you know, just sort of taking baby steps the way we do in science, we can improve our models and improve our understanding of, you know, I think like Jan said, like asking the right question and hopefully you know, develop models that can actually give us useful results on real data.
Well, I think deep learning requires a lot of data. That's the very first requirements. So in terms of EPRV, in terms of the time series, we not have as many data, but in terms of the data obtained from each observation, it's a lot because it's basically a whole spectrum of a star. But whether we can make use of this spectrum obtained at each timestamp for disentangling stellar variability from exoplanets, I think we might still need more physically motivated models to train the neural network.
I agree. And I think the most promising aspect of using deep learning in mitigating stellar activity is that it does not require you to pick an RV quiet star to look for Earth twin, because there are just so many nearby stars and you cannot ask them to be quiet. So yeah, so deep learning allow you to model things that you understand and things you do not understand. This is the most promising part. And it's, of course, very challenging. And I think physically informed model will be the way out. Adding physical intuitions and knowledges to models can greatly reduce your parameter space to search and help you find the correct answer.
I think one of the great advantages of deep learning or machine learning in general is the ability to work with a lot of data and in a more easy way and a very optimal way. So I think it's a good way to start. It's a good way to work.
So there was a lot of discussion about like also wanting to add like some more physically motivated models into the machine learning methods. So one question that we also had thought of is what are like some of the limitations that you see of using these kinds of methods, or how do you think maybe they should be augmented, for example?
I think the conclusion is the same as the first day. Interpretability. It's a problem. We don't really know what happened inside. If we want to see what happened, it's another paper, right? It's another big paper to try to understand. So maybe I think this is the best. This is the most difficult part, I think.
And I feel the same. Interpretability is the biggest issue. Not only for discovering things, but also to convince people that we've discovered things. So last year in December, I went to a machine learning workshop, and I saw a lot of people discussing if you can make physical discoveries using machine learning understandable or convincing for other people. I think we are on the right track, that there are a lot of methods to open your black box. For example, I'm trying to use a interpretable latent space to open the black box. It's not done yet, but we're going to be there.
I don't have an answer for this question, but I think we can do something indirectly to move closer to the answer. Like say, in terms of spectrum, the radial velocity information lies in the mostly in the wing, like because it's great, it has a larger gradient. So when we do this feature injection, we can just select the information that contains the information of what we want to recover. So instead of like putting the whole 1D spectrum, for example, that includes the continuum. We can just select some features that are more sensitive to what we want to recover, or as the example that I showed, using Fiesta that can parameterize the line deformation and extract the information that is not sensitive to the line shift. So,
it's important. I think another risk of machine learning is you could make a lot of mistakes and you never notice, and your colleagues also never noticed. There was a paper, I think, a couple of months ago. They review 300 papers of machine learning, and in more of the half of them, they couldn't reproduce the results because of these mistakes, right? I mean, I can do train validation and test, only use testing for the final result, etc. But depending on the problem, I can leak information from the train to the test, right? And I never notice. Even Andrew and G, the machine learning god, make that mistake in one of his classes. So it's very troublesome. You can make a mistake and never notice.
Yeah, I think that's one thing we worried a lot about, like with injecting RVs. And that's why I don't know if it's perfect or not. We actually haven't, this is something that we need to look into more, but when we inject the RVs, we do it at the same time as the barycentric correction. So it's like, well, we figure we have to do an RV shift anyway on the real data. And so let's just add a number to that. And, you know, that's sort of the least damaging way of doing that, hopefully. But, you know, the information is still being injected by us of what, you know, into the spectrum in a way that isn't perfect, you know, because then we're interpolating. So, and so it's, you know, there's always that risk. And yeah, I just wanted to give that little story to talk about how we, one way that we've, one problem that we've had with that. But the other thing I wanted to add to this discussion of physically motivated models is that when you inject RVs, you are giving it a physically motivated model. You know, an injected RV is like, you know, you're trying to do it in a sort of perfect shift sense. And that is a physically motivated like model of how the stellar spectrum shifts. You know, you might not be including the differential shift between the telluric spectrum and the stellar shift, and there's some other complications there, but you know, we are to some extent, you know, able to just incorporate physical models directly into our construction of these methods.
Audience questions. Any audience questions? Yes, okay.
So on the first day of the conference, Suvrath laid down the war between the people who want to understand the physics and the people who want to understand just, you know, give me the answer with the data. You would think that we in this room would be on team data, but it sounds like all of you think that physics has its role. What's the balance that we strike, and how do we incorporate it into our models?
Who wants to start?
So I think physics is very important, and physics can help us understand what our methods are doing. For example, if it's say my machine learning method discovers a new planet, I will ask for follow-ups. So if it can be confirmed independently using other traditional methods, so to speak, then it confirms that machine learning method works. It's more reassuring to us and to the rest of the community. And I think one of the brightest possibility is that your model can discover something new that can be also studied in a traditional way. Say you find a new type of activity and you can find physically motivated models for that activity. So I think it's not a balance, but it's cooperating and try to come up with a more comprehensive story for your findings.
As a computer scientist, I think I don't care about the model. I just give me the problem and an input, I generate an answer. But I think if someday I find something, I will start to looking for the model, or at least try to interpret something, because I don't think it works. It doesn't mean nothing if I can get an explanation.
I will make a specific example of one of my thoughts of my future research. So let's say we want to disentangle the planetary Doppler RV, but because we don't know what it is, what the RV is, but then we can have a model for the planetary Doppler RV, and let's say we can subtract this model of planetary RV from what we observe as the total RV, and also the activity indicators that we can derive. And then what is left would be the time series of the stellar activity RV, and also the indicators that is sensitive to the stellar activity. So we can use these leftover activity indicators to feed into a machine learning model to predict the stellar activity RV. So I think in this sense, we combine our physical understanding of what a planetary model is, and also the machine learning black box in solving the problem.
Yeah, I don't think I have much to add other than I think, yeah, you just have to take do your best, right? I mean, we all want to understand the physics better, and we know that that's where the real leaps and bounds happen as far as progress. But sometimes you do have to throw your hands up and be like, all right, maybe a computer can figure out what the parts that we don't understand, and try to limit your approach to that.
Hi. I think there's a lot of people who are very interested in machine learning, but like myself, maybe don't have time to dive in and just really get in the weeds of it. But we want to understand what's coming out of other things. We want to maybe take some of these tools that have been made and use them for ourselves. How do you guys think we can structure our tools and our publications and our code repositories to make machine learning and reproducing results more accessible to people who aren't deep in the weeds of machine learning, and tackle that problem of reproducibility?
Sure, I think we should fund software development more than we do. I think most people in EPRV machine learning are funded as some sort of algorithm development, or some sort of like research as for, like, towards new methods for mitigating cell activity, but not specifically for developing a nice package on GitHub that has a README and a tutorial. And I think that those things should be prioritized in proposal committees, and maybe even specifically mentioned in EPRV calls to make these tools actually more accessible.
I think I agree with Alex, and I also think that in terms of practice, it would be easier if we have some templates or something that we want to start. Let's say we want to start a project, we can just fill in what we think specifically on top of what the template has to offer, so that it would be easier for us to reproduce these tools as a whole.
I just want to emphasize that it's pretty straightforward to create a repository on GitHub, just upload and README. And I would encourage everyone who's working on machine learning plus astronomy to make your code open source. Otherwise, people would not care. They will care only if they can reproduce your results. In particular, I collaborated with a professor in the computer science department, so our code was made public. I benefited a lot from managing things on GitHub, so it's not that hard. Take an introductory lesson or something in 10 minutes, you will figure out how to use it.
I think it's a really good question. First of all, if you want to start with machine learning, it's like a toolbox with 200 of tools, different tools. So you have to focus your you will work with some problem. You will find the right tool. For this particular case, all the papers I read, they always build from ground up the tools, because you can have a trained network. I mean, for the bigger problems, you can download a trained network and use it. But are for the bigger problems in LLP or image recognition. So for these particular problems, there's not. So I didn't saw anything close, so you can use it. So I think the GitHub solution is the best one. For example, for Exoplanet, I put the compiled network in GitHub and some periodogram to test, and so try with a notebook. But I think for now it's the only solution I see.
I just want to add a little bit more. So regarding to your question, like how to get it started, I think it's best to define your question, whether you have a project in mind that you want to solve, whether it can fit into the machine learning aspects. So for my project, at first I wanted to, let's say I started with no idea about like what machine learning is about, and then I just wanted to like get involved into a machine learning project, and I talked with an assistant professor at Penn State, Ashley, and then I wanted to like get involved with one of her projects. She actually does a lot of like supernova light curve studies and characterizing different supernova, but she then suggested me that try to figure out if I have something in my project that will require machine learning, and that would be a lot easier for me to pick up. So that's what I did. And so I would suggest that if you have an idea of what you want to do in your research, and see if it can fit into the machine learning aspects, and then it will be easier to get started.
I think one thing I'll just add quickly is like, if you maybe don't have time, like you said, to learn all the machine learning stuff, I think another thing is like maybe just being kind of familiar with like what kind of things do people check to make sure that such a flexible and powerful model isn't like overfitting on your data, for example. So even if you don't necessarily want to learn the ins and outs of what's a neural network, you might just want to like look at like, oh, did they use some kind of cross-validation? Did they have some kind of test set that's separate? And does like the model perform equally well on those separate data? Or did they use some kind of other like regularization method to prevent overfitting? So it's like, even if you don't know the specifics of what's an autoencoder or what's a neural network, you can still kind of check these general like things of like, did they take precautions since it is such like a flexible method? Okay, other audience questions? Yes.
So we talked about interpretability. So I was wondering if like in your experience so far with the EPRV community, have you seen like certain types of metrics or tests like sanity checks or any type of like what has helped in communicating the results to the community, and yeah, what has worked and what hasn't worked?
It's easy. I didn't see anything. I didn't saw anything. No, I didn't saw any check or something. No, I don't know if someone saw any check or something like that. No.
It's related, but might not be a sanity check. You can try to leave one point out and see if you can recover or predict that one data point. This is the closest thing that I can think of.
Plot the loss function, like the loss function as a function of the steps of training, and so that you can see like how the loss function involved for a training data set and testing data set, etc. That's probably one of the ways you can do it.
Yeah, I feel like maybe it's also because machine learning methods are only newly kind of being applied in EPRV science that we probably don't have a ton of like standard sanity checks besides just like general machine learning sanity checks. But probably an area that we should think about more. Other audience questions? Yes.
So as you were just saying, in fact, machine learning is kind of newly being adopted by EPRV people. And, you know, there's been a lot of previous research and development in fields that aren't even physics necessarily. Are there any practices from computer scientists or other software engineers or whoever's been using machine learning previously that you really find you don't agree with should be used in EPRV at all? Like some practice that, yeah, people at Google love to use, but has no place in EPRV.
No, I don't think so. I didn't saw any strange practice. In fact, I think I need to use more that practice. I think like this one I said a couple of minutes ago. You could. It's very difficult to see if you leak information to the testnet. The rule says you divide your data into test. You put the test in a drawer, you close the door, you never touch it until the very last end, and you do cross-validation, etc., etc. But the example is, let's suppose you are doing a you are classifying, you're taking pictures and saying is